AP chemistry curriculum, the common ion effect. The common ion effect refers to the way that ionic compounds dissolve in water versus how they dissolve in a solution that contains an ion present in that ionic compound. For instance, if we have the compound copper 1 chloride, CuCl, and it's a solid, and we try to dissolve it in water, the copper ions and the chloride ions will dissociate from one another, and they'll produce Cu positive ions in aqueous solution, and then they'll also produce chloride ions in a 1-to-1 ratio because that's their ratio in the compound. So for every copper ion that's produced, a chloride ion will be produced. However, if we take the same copper chloride ion compound and we place it in a solution that already contains copper ions or already contains chloride ions, then the copper chloride will not dissolve as much because there is a common ion already present in the solution. So less of the copper chloride would actually be broken apart by the solution because of the presence of an ion already present. For instance, if we already had some NaCl in the water, NaCl has the common ion chloride. And so that chloride is going to keep the copper chloride from dissolving to the same extent it would in pure water. That's what the common ion effect has to do with, is that if a compound is dissolving in water, if there's already a common ion present, it will dissolve less. You can think of this in terms of Le Chatelier's principle. If we dissolved copper chloride into pure water, we would make the copper ions and the chloride ions, and they would reach an equilibrium, a maximum amount that could be dissolved. However, if we then added some chloride ions to the solution, then that extra chloride would force the equilibrium to shift to the left. In other words, you would have less copper chloride dissolving in the solution because of the extra stress of adding the chloride ions. So the same would be true if chloride's already present. That's a stress already present in the solution, so less copper chloride would dissolve. So we're going to go ahead and see how this plays out in a practice problem where we'll see what is the solubility of copper chloride in pure water versus what is the solubility of copper chloride in a solution that already contains chloride. So here is our example. What's the molar solubility of copper chloride in pure water versus copper chloride in a solution that is 0.01 molar sodium chloride that already has chloride present? So to do this, we're going to create a rice table where we show our reaction or our process of copper chloride dissolving, which we just did. So I'm going to go ahead and write that again. Solid copper chloride dissolving into copper ions plus chloride ions. And that says AQ, sorry for the bad handwriting. Then initial concentrations, our change in concentrations, and our equilibrium concentrations. So we only care about substances that are aqueous. And so initially, doesn't matter the copper chloride. We're just looking at what maximum amount of copper chloride could dissolve. Initially, we will have no copper ions present, and we will have no chloride ions present. So it'll be 0 molar in copper ions and 0 molar in chloride ions. Change-wise, we're going to have some of the copper chloride dissolve, and the maximum amount that will dissolve and reach equilibrium is X amount, and chloride will be X amount. So we will gain X amount of each one. So at equilibrium, we will have X molar copper ions and X molar chloride ions. They have to be the same because it's a 1-to-1 ratio of copper ions to chloride ions. Now, if you recall, equilibrium concentrations relate to the KSP value for dissolving, the solubility product. So KSP is equal to concentration of copper ions times the concentration of chloride ions. KSP for copper chloride, if you look it up in your book or on a table on the internet, is 1.7 times 10 to the negative 7. And that's going to equal X concentration of copper ions times X concentration of chloride ions. Just a reminder, the exponent on these is the coefficient. So both of these have a coefficient of 1, so they both have an exponent of 1. If one of them had a coefficient of 2, then we would have to raise the exponent to 2. But in this case, it's a 1-to-1 ratio, so it's just an exponent of 1. So if you solve this for X, you will get 4.12 times 10 to the negative 4 molar, meaning that when we dissolve copper chloride in solution, the maximum concentration of the ions of copper ions and chloride ions will be 4.12 times 10 to the negative 4 molar in pure water. So I'm going to write this over here just to remind us that that will be the concentration of copper ions. Oops. The concentration of copper ions will be 4.12 times 10 to the negative 4 molar in pure water. Now we're going to redo this process, but instead of putting it in pure water, this time we are going to dissolve it in a solution that already contains chloride ions. So a 0.01 molar sodium chloride ion solution. So again, initially we don't care about the copper chloride, but this time we have no copper ions present, but we do have an initial amount of chloride ions from the sodium chloride. It's 0.01 molar. So that's going to affect our equilibrium concentrations because we already have some chloride present. So for change, we are still going to gain X amount, X molar copper ions and X molar chloride ions. So at equilibrium, there will be X molar copper ions, but this time 0.01 plus X molar chloride ions. Because our KSP value is 100 times less than our initial concentration of chloride, we can ignore this plus X, which will make our math much easier. Because again, the concentration of chloride is more than 100 times the KSP value. So now plugging in our KSP, which is 1.7 times 10 to the negative 7, times the equilibrium concentration of copper ions, times the initial concentration of chloride ions, or equilibrium concentration, not initial, sorry. So X times 0.01. If you solve for X this time, you get 1.7 times 10 to the negative 5 molar. So this time, because there was some chloride present, notice that we have much less of the copper chloride dissolving, 1.7 times 10 to the negative 5 molar, as opposed to in pure water when it was 4.12 times 10 to the negative 4. So this quantitatively confirms that the common ion effect causes less of the original ionic compound to dissolve. So that's the common ion effect. I hope that was helpful to you. If you have any questions, of course, ask me in class and I'll be happy to help you out.